Hi, I'm Brandon Hargis with NASA Langley Research Center and the Aerospace Education Services Project. I'm here to talk with you today about Spacecraft Structures, an engineering design challenge. It's part of the Summer of Innovation modules. Our training module objectives today are to provide an overview of the lesson activities, to describe and show an illustration of the launch apparatus, and explain the materials used in the activity. I hope to provide some direction for successfully conducting the lesson activities. The Engineering Design Challenge of Spacecraft Structures is for students to use creativity and scientific knowledge to solve a real-world problem faced by the space program. And hopefully they'll be using and learning about forces, motion, and structures along the way. Every pound that's carried to space requires fuel to do so, regardless of whether that pound is cargo, crew, fuel, or part of the spacecraft itself. The more the vehicle and the fuel weigh, the fewer passengers and smaller payload the vehicle can carry. Now, designers try to keep all parts of the vehicle, including the skeleton or the structure, as light as possible. Now, to design a lightweight structure is very difficult, because it must be strong enough to withstand the tremendous forces, the thrust of the engines during liftoff. This particular engineering design challenge focuses on the Ares 5 heavy lift rocket's thrust structure, which uses 5 liquid fuel engines at the base of that rocket. And students will be representing that with the bottles that you choose for them to use. Now, as part of this challenge, they'll be using the engineering design process, and students should be working in cooperative groups of 3 to 4. As part of this cooperative group, they'll be identifying the challenge that you give them. They'll then need to brainstorm ideas, sketching them out on paper, labeling the parts of their model, as well as looking for weak areas prior to building the models themselves. Once they've built a model, they'll then begin to test that model to see if it can meet the challenge that you've given them. They'll then refine that design and continue to test and refine their designs throughout the sessions that have been set aside for testing and refining designs. The last session, they'll provide you with a storyboard and presentation of their findings, as well as a journal that they've kept along the way. The design challenge itself, you will present students with this challenge to build a model thrust structure, the portion of the structure that attaches the engine to the rest of the spacecraft, that is as light as possible, yet strong enough to withstand the load of a launch to orbit 3 times. Their design constraints are to use only the materials that have been specified in the materials list, and of course you can add or take away to that list prior to the activities starting. They also need to build a thrust structure that is taller than 2 inches or 5 centimeters, and they must allow space in the center for fuel lines and valves, which can be represented by a 35 millimeter film canister without its lid. Now, this film canister doesn't actually stay inside the thrust structure when they launch, but it should be inserted prior to testing or prior to launching so that we can determine that they did follow the design constraints and leave that space. You'll see in the figures here teacher demonstration models. The first is a paper cut model with a simple piece of cardboard on the top, and this one is to represent a lightweight structure that is unable to withstand the forces. So you can test this for them and show them the compressive force and how it destroys this particular structure. The second figure is an overly built model that you can provide ahead of time and demonstrate for the students, a model that can withstand the forces of launch but is nothing near lightweight. Students would be challenged to build something that's much lighter than what you have built for them. And there are information in the guide on how you can put these two models together. Now I really want to show you the apparatus. It's something that you would need to build, and you will need to acquire some materials from a local hardware store in order to put this together, but it's fairly simple. It can be built in 10 to 15 minutes. You'll see that it's a simple lever system. There's a ring stand on one end. You can use two ring stands, but one is enough. On the other end, you see a drop height is given where you're dropping the bag that's filled with sand. You can choose any amount of weight for that bag. However, 22 pounds is a good weight because it can easily be converted into kilograms, 10 kilograms, and you can then use that to solve equations of mass and force with the students after the activity. You may also decide to use something other than sand, and that's perfectly okay too. It should be able to move loosely and deform upon impact. The lever itself is built with a 2x3 piece of hardwood, and it can also be a 2x4 if you're unable to find a 2x3. It's about 50 inches long, and it's attached to a mounting block, which can be a piece of that same piece of hardwood, with a T-hinge. Now that T-hinge is attached with flathead wood screws, and you want them long enough to make it stable, but not so long that they poke through the end of the wood. All of that's attached to a plywood base. It's about 10 by 14 inches in size, but it can range from any size from 8 by 12 and on up. You just want it to be stable as it's sitting on the ground. On the business end, you have the water bottle rocket, and I'll show you a slide of how that's put together. And sitting underneath that is the thrust structure that the students will be building. That thrust structure will be placed there each time, and it should be placed in a way that all 5 lobes of the bottle, the base of the bottle, rest on the thrust structure itself. You will need someone to drop the bag of sand and another person to catch the bottle, and it takes a few minutes to determine what the right height will be based on the weight of the sandbag that you use. You don't want the rocket going so high that it's hitting the ceiling or that it's a danger as a falling object, but you do want it to reach at least the 3.3 feet or 1 meter height above, which is the height above the ring stand. The bottle itself is a simple 1.5 liter bottle with a 5-lobe base. You may use smaller bottles or provide smaller bottles for students to have a choice. In an inquiry-based lesson, they would have choices as to which bottles they wanted to use. You can have a 2-liter bottle as well. The bottle is put together by taking a piece of brass tubing and some clear packing tape, attaching that to the bottle, filling it with water, and then you would want students to measure the mass of that full water bottle rocket as well as the mass of their thrust structure prior to launching and testing their designs. There are some forces at work in this activity. You can see in the figure 1 on the left side there are no compressive forces in this particular example because the thrust structure is merely resting on the hardwood board end of the lever, and the amount of force pulling or down by gravity is equal to the amount being pushed up by the lever, so it's balanced forces and there's no compressive force. However, on the other side of the slide you see examples of compressive forces at work where a person is squeezing the thrust structure between their two hands, and in the bottom when a sandbag is dropped, the amount of force pushing up on the thrust structure in the bottle is greater than the amount of force pulling them down, and in that case you will see an acceleration of that bottle and the difference of those two forces. In this case it's 0.1 newtons. In my last slide you see another example of forces during acceleration, and in this case the lever is accelerating a car with a force of 2.5 newtons pressing against the car is pressing back at 1.5 newtons, and that leaves us an acceleration of 1.0 newtons. So this is an example of some of the equations and math that you can do with this activity as your students are learning about forces and structures as well as acceleration and motion. I want to thank you for joining me today for this Summer of Innovation module for engineering and the Engineering Design Challenge Spacecraft Structures. I hope you enjoy working this activity with your students, and I wish you luck.